Okay, welcome. Welcome. This is the week 9 webinar of the class. We're getting close. The light is at the end of the tunnel. And I want to, as always, talk about the plan. So feel free to ask any question you might have throughout, and I'll be happy to, do my best to answer it. And then after that, actually, chapter 11 is what we're going to be looking at, is all about chi-square distribution. So we're going to be looking at the chi-square distribution and kind of seeing that's kind of a new distribution that we haven't played with yet. And we'll kind of see what it looks like and talk about it. And then we'll get into hypothesis testing. As I mentioned, as I promised a few weeks ago, the rest of this quarter, we're going to be doing hypothesis testing every week. And this week, that's all we do. We're going to do hypothesis testing. And in particular, we're going to do hypothesis testing for something that we haven't really approached yet. We've defined it, but we haven't learned how to analyze it. And that is when you have a qualitative survey question that isn't just a yes/no question. And sometimes it's comparing two qualitative survey questions answers. And we'll be looking at that. So there's going to be 3 different types. The first will be the chi-squared goodness of fit test. And the chi-squared goodness of fit test is very important. It happens in lots of applications, and we'll see some of them. Then we'll look at the chi-squared test for independence, and that basically decides whether 2 quantitative things are independent or dependent. Okay, and we'll see, and we'll have a hypothesis test for that. And then finally, we'll talk about the chi-squared test for homogeneity. And that basically compares 2 different groups to see if there's a difference in their qualitative answers. And that pretty much is what this whole thing is all about, is the chi-squared test. So I do want to remind you that, again, we're in week 9. It's an odd week, so there isn't a project due. So I strongly recommend putting a lot of your effort this week into project 2. Because we're in week 9, project 2 is due at the end of week 11. So 2 more weeks, 2.5 weeks, I guess. And you'll have to submit your project. And there's a lot to do on it. So you want to make sure you get it done. And of course, you have to, if you have questions, you should ask them, get help from me, send me your draft, all that kind of stuff. So that is important, is thinking about your project. So let me ask, are there any questions about anything before I talk about chi-squared? And again, feel free to ask any questions you might have. And I'll be happy. I'll always have one eye on the chat box, and I'll be happy to answer any questions you have. Okay, if there aren't any questions, then let's look at the chi-square distribution. And it turns out, let me do it this way. If you go to the calculator and you go back 1 to interactive statistics, then you can actually go to all kinds of different things. And one is visualize the chi-square distribution. So this is a distribution we've learned about, for example, the normal distribution, which is symmetric, kind of looks like a bell. We've learned about all kinds of others. We learned about the t-distribution, which is kind of a spread out normal distribution. Learned about binomial distribution. So we've had some distributions already. And the next one is going to be the chi-squared. The math in pretty much all of these is way too hard for me to explain in a webinar, and you need like intense mathematical background. So don't worry about the mathematics behind it, but I just want you to see a picture. So here is the shape of the distribution. It turns out, just like the student t-distribution, there's something called the degrees of freedom, and you get a different shape depending on the degrees of freedom. So here's df for degrees of freedom, and that is 5 right now. And you can see that this is not a symmetric distribution. It is skewed right. The other thing you might notice is that it doesn't go past to the left of 0. there's no negative values, and kind of the math behind it has to do with the with the name, actually, chi-squared, because there's a square involved. And square number, you don't get a negative number. As long as you have to square any real number, you get a positive number. So just to note that you only have positive numbers, so we're not going to have a left tail. We're only going to have a right tail. So that makes life a little easier. There's only a right tail test. So that's a big deal. If we change the degrees of freedom, let's say we go to 2 degrees of freedom, then it's very skewed right. It goes way up near 0. You can kind of see that. If you change it to very many degrees of freedom, like 18, it gets a little closer to being normal, but it does, you can't see it, but it literally stops and becomes 0 at 0, and it doesn't ever become 0 to the right. But that's a chi-square distribution, and that's the distribution that we're going to be using for everything we do in this week. And in particular, if you have a distribution and you had, say, 5 degrees of freedom, and let's suppose your test statistic was 10, then the area to the right of 10 will be the p-value, just like we've had before. But now, again, we only do right tail tests of the chi-square distribution. Any questions about just kind of the idea? Okay, if there aren't, then let's go look at examples. So by the way, this chapter is not one of the harder chapters. Most people do not complain about it. But you still want to pay attention, and that's important. We might even have a shorter webinar because it's not a super long chapter, but we'll see how it goes. And just one more note, because it's sitting here looking at us, and that's this. This is not an X. This is actually a Greek letter that is called chi. C-H-I is how you spell it in English. And the way you spell it in Greek is right here. And then squared. So this is how you write chi-squared, is you write the Greek letter chi, and then you do a superscript 2. And just let you know that if you're just typing it without any like knowledge of how to do fancy stuff, then you'll probably just want to write CHI and maybe SQ for square or something like that. You can go into Canvas and you can go into the equation editor and go to the Greek letters and find it. That's a choice too, but there's a note in terms of finding it. I want to make one more note about the chi-square distribution that's important, and that is if you use it for project 2, you screwed up. Project 2 is not about the chi-square distribution. It doesn't go anywhere past chapter 10. So we're in chapter 11 now. So don't even think about mentioning the chi-square distribution. So let's go and look at an example. So here's an example. And that is in California, 40% of residents are Latino, 30% are white, 15% are Asian, Pacific or Pacific Islander, and 10% are other races. Okay, that's just what we are. You could look that up on Google or whatever, and you'll find that that's true. So a question you might have is the distribution of races different for California community college students? Okay, because one of the things we like to do at California Community College is we want to make sure that we are helpful to anybody, no matter what race they're from. So we're hoping that anyone in California would come into the California Community College system. So it'd be nice if we didn't have a different distribution of races. So that'd be a question you would have. Okay, a survey was done. And when I say a survey was done, I'm actually making this up, but you can imagine a survey could be done of 300 California community college students. 125 were Latino, 92 were white, 33 were Asian or Pacific Islanders, and 50 were other races. What could be concluded at the 5% level of significance? So notice what's real different about this is if you think about the survey question, the survey question would be, what is your race? So let's see if you can put in the chat box. If you don't feel comfortable, you can always make something up, but hopefully you do. I'm white, by the way. Write down the answer to what is your race. And put it into the, by the way, this is not being recorded, what you write. Okay, so you'll notice that all of you did not write a number like 73, okay, because that's not a race, by the way. You didn't write yes or no, because that's not a race either. You wrote one of these things, and you either wrote Latino, you wrote white, or Asian, or Pacific Islander, or maybe other. So the answer to the survey question is completely qualitative, and it's not a yes or no question. Any questions on that idea? And we have not ever touched on how to do an analysis of a purely qualitative, not yes, no variable. And that's what we're doing today, is how do you make these analyses, statistical analyses? And this isn't just like one weird question that, you'll never see another. There are so many surveys where you're going to have a qualitative not yes, no answer. Very common. The survey question, I actually said it out loud, and you answered it. The survey question is, what is your race? Isn't that the survey question? Does that make sense? That would be the survey question for you. What is your race? And it might even be, what is your race? Latino, white, Asian Pacific Islander, or other. Okay, it could be, that way also. But either way, it is very qualitative. Okay. Any questions at all on that example? All right, so here are the steps that we're going to have to do. So step one, we already did, and that is read the question. And I hope you all know how to read. That is a requirement of this class. So we read the question. Step two is look at the variable and decide what kind of variable is it. In this case, we just did that, and we decided that the variable for this particular survey question is a qualitative not yes, no variable. And notice it's just one survey question, and we're only looking at one group of people that we don't know, and that is the group of California Community College students. So that is important to note. When we're in that situation, then we're going to be using what's called the chi-squared goodness of fit test. So we'll see what that means and why we use those words. Goodness of fit, chi-squared, because that's the distribution you'll end up getting. And by the way, you're never going to see the math unless you decide to change your major to math on why and what chi-squared is about mathematically. I just showed you a picture of a graph. Next step, and you're used to doing this, is you write down the null hypothesis and the alternative hypothesis. Now, I want to give you a big heads up. Some of you didn't listen in the other webinars, but for chapters 9 and chapter 10, your null and alternative hypotheses must be in symbols. I mentioned that last week and the week before, that you do something like H naught, mu equals 7. And you don't write down some long sentence. Okay, chapter 10, you might write H naught, P sub L equals P sub W. It's not one big long sentence. So that's something to note. Don't change it when you, for example, do the project, to make sure that you can do it in symbols. I did grade your exam already, and I did notice that some of you did not put your null and alternative hypotheses in symbols, and yeah, you lost points. And I promised that points would be lost during the webinar, I think 2 weeks ago. So on the other hand, for chapter 11, the null and alternative hypotheses will be sentences. So let me show you what they are in this case. So H naught make this bigger so you can see it better. In this case is the distribution of races at California community colleges is the same as the distribution of races in California. Okay. H1, the alternative hypothesis, is the distribution of races at California community colleges is not the same as the distribution of races in California. Just note, I highlighted the word distribution, okay? Try to really scream it out. And hopefully you know by now, because I say this in like every webinar, why did I highlight it and scream out the word distribution? Hopefully you all know. I want to make sure that all of you have this down so you don't blow it. So why did I highlight it? Put it in the chat box if you want. So write it down, understand it. That's a piece of it. But even more importantly, just to make sure that you're aware of this, if you do not put the word distribution in your H0 and H1 for a goodness of fit test, you will lose points. Got it? That's a promise. And by the way, if you do write down the word distribution, you'll gain points. You won't get a 0. That's for sure. As long as you have that word. Doesn't mean you'll have 100%, but at least that's a piece of what you have to do. Any questions on that? Okay. Also note that H0, and we're used to this, H0 for chapters 9 and 10 always had an equal sign. Do you remember that? And the words for the equal sign is the same as. So that's why I put in the words is the same as, because that's equal. Okay. For H1, I just wrote is not the same as. I put the word not because that's kind of the reverse of is equal. Okay. And again, we don't have a left-tailed test. That's not happening. So it's either all or nothing. It's the same distribution or it's not the same distribution. I do want to mention that we will never accept H0. Don't ever go there. I noticed that in some of the exam question of your answers, you accepted H0 and you lost points. Okay, don't accept H0. Okay, and some of that accepted H0 was interpreting the type 2 error. You don't accept H0, you fail to reject H0, which is not the same thing as accepting. Any questions at all on H0 and H1 and how I came up with the verbiage of these? Okay, one nice thing, especially with an online class, once you write down H0, all you do is go like that, copy, and then you can go to H1, paste, and then put in the word not. So for typing, it's a lot faster to do it that way. Just let you know that. Any questions on that idea? And we're going to be doing a lot of that for the rest of the class. This is a copy and paste idea. Okay, so we're used to this. After you find H0 and H1, then you're going to probably decide on the p-value. This is definitely sociology. P-values, I'm going to use 0.05. You could look at the type 1 and type 2 errors and look at that too. And then, hopefully you're used to this too, after you find, you decide on level of significance, then we go and find the p-value. So we found the level of significance, we find the p-value. To do that, we're going to have to decide the test to use. And the test we're going to use is the goodness of fit test. And often I'll ask you, what test should you use? And in this case, this is a goodness of fit test. Okay, and that's because the goodness of fit test is used when you have a known distribution Then you take a sample of a population that you don't know the distribution of, and you want to see if the unknown distribution is the same as the known distribution. Here we know the distribution of California because that's given, we know it. We don't know the distribution of community college students in California. So that's why we use goodness of fit. Any questions on that? Okay, so the next step is we're going to calculate what's called the expected values. So let me make this bigger. So we're going to calculate the expected values. Okay, so the idea here, if we surveyed 300 California community college students, and if we said the null hypothesis was true, then we would expect 40% of them to be Latino. Does that make sense? So I take 40% of 300. And by the way, that is 0.40 times 300. You could use a calculator, or I just did it in my head, but you might want to use your calculator. That gives you 120. So that's going to be for the Latino. For the white, we would expect 35% to be white. That's going to be 0.35 times 400, times 300. And if you work that out, that is 105. Okay. For the Asian, 15%, that's going to be 0.15 times 300. And that's 45. And then finally, for the other 10% or other races, that's 0.10 times 300. And that's 30. Any questions on that? Any questions on how I calculated the expected values? Okay, this is different than the expected value that we got in chapter 3. Chapter 4. This is the expected values for goodness of fit testing. Then the next step in this process is to create a table. So here's how the table works. For the columns, you write down all the possibilities for the survey answer. We have Latino, we have white, we have Asian Pacific Islanders, and we have other. For the rows, I'm going to write O for observed and E for expected. Any questions on the table? And then I put my numbers in. So the observed was given. Notice we observed 125 Latinos. So an observed for Latino, 125. For whites, we observed 92. So 92. For the Asian Pacific Islanders, we observed 33. So 33. And then finally, for the others, we observed 50. So I type in 50. Any questions on the row for the observed? Okay, the expected, we just calculated all that. So we've got the numbers. The expected for Latino was 120. The expected for the white was 105. The expected for Asian Pacific Islanders, 45. The expected for the other was 30. Any questions on that? Okay, so it's very much a step-by-step process. Sometimes, by the way, you'll see observed and expected as columns and the answers as rows. Really depends on just how much space you got. So for this particular page, it made sense to do it that way because it fit nicely. So it's your choice on, rows and columns, but make sure when you put in the calculator, you understand, how to do it. We need to find the test statistic, which is chi-squared, by the way. And we need to find the p-value. Any guess how we're going to do that? How do you think we're going to find the test statistic and the p-value? Here's the hint. It's a much easier way than when I first taught this class 30 years ago. Yeah, but it needs a calculator. 30 years ago, it all had to be done by hand. It was miserable because these statistics calculators didn't exist. Obviously, I hadn't made mine, but there really weren't any. So we're going to go to the calculator. And I want to let you know we do things in order of the class. So which calculator number do you think we're going to be using? Yeah, 21, because we've already determined that we're doing a chi-squared goodness of fit test. So I'm going to do goodness of fit. And notice what it asks for is the observed and the expected, and separated by commas. Computers do much. I did that. It's actually easier to type if you do it that way. It'll be faster for you to separate them by commas than make it a table. And especially if it's given, because what I can do is literally I can copy the observed table, Control C, and then I can paste it and then put commas in between. That's a lot faster than having to type them individually. And then the expected, same thing. I'm going to separate them by commas. So I can copy the expected. And then I can paste them. Any questions? And then make commas in between. Don't forget the commas, by the way. Any questions at all? Okay, and it's very simple. Again, it's not like you have to decide whether it's a left tail or right tail or two-tailed test. There's just one kind of test with chi-squared. So I just hit calculate. And there we have it. Our chi-squared is 18.35 or so. Okay. So let's do that, 18.35. And our, whoops, after the equal sign. There we go. And the p-value was about 0.00037. And by the way, I did that last winter. I made it pictorially so you can actually see the chi-squared distribution. And you can see kind of the points for the level of significance. If we used a level of significance of, say, 0.1, that's here, you'd have to be anything to the right of that, you get to reject the null hypothesis. And you can see it for the 5% and the 10%, and you can see where we are, way, way over here, 18.3 or so. It's way down here. Okay, so it's really, hopefully really clear what to do. So our p-value is really tiny. So what do you get to conclude when the p-value is really tiny? When the p-value is really small, what does that mean? Yeah, there's strong statistically significant evidence. Maybe I'll just type it out here. I also have it below too, which you haven't seen yet. There is strong statistically significant evidence to conclude that, and here's the cool thing. All I have to do, copy and paste my H1 sentence. And Maybe I'll even do this to make it pretty. There we go. There is strong statistically significant evidence to conclude that the distribution of races at California Community College is not the same as the distribution of races in California. Any questions at all? Any questions at all on the conclusion? Okay, just let me ask you something. Based on this, can we say which is the big different one? Is it because there are a lot more Latinos than you would expect? Or maybe because there's fewer Asians that you expect? I mean, what do you think? Could you do that? Can you make that conclusion? Any thought? Because hey, we observed 125 Latinos and we only expected 120. So there were more Latinos. So can you observe? Can you say that, hey, there's, the reason is because Latinos are overpopulated? Can you say that? Any thoughts? Okay, the answer is definitely no. You can't say that from this test. Okay, if you want to be able to delve deeper into this and figure out which is the race that really is different, that's made this a different distribution. Any guess on what you have to do? And from now on, I'm going to be saying this a lot. Any guess? I don't see y'all guessing. All right, let me tell you what you have to do. What you have to do is transfer to a university and take their upper division statistics class. Advanced statistics. This is an elementary statistics class, so we can't do everything. And that's one of the things we're not going to do in this class is kind of look at this and decide which are the ones that are different. But there are statistical tests that can help you learn how to do that, but you need to take advanced statistics. Okay, and that's going to be true of a lot of things we're going to be talking about from now on. Okay, any questions? Any questions on this? What's the name of the test you're going to have to take? Advanced is the Tukey analysis test. There's a few others too. It depends what you're doing. And again, way too advanced to even go over which is which and how to do it. So there's lots of tests, and it's too complicated. So aren't you glad we're in an elementary stats class? But there are tests to use. All right, so here's the next question. Does it matter what season a person was born when it comes to the type of car they drive? Table below shows the season and car type. So what do you think? Do you think it matters? Do you think if someone, if you were told what season they were born in, spring, summer, winter, or fall, then you have an idea of what their car might be? Okay. Okay, I would probably say no, but hey, you might be one of those who believe in astrology. And hey, you look at your birth sign and that tells you everything about who you are. But you never know. And the way you decide is actually, this is not about correlation and causation. Next week we'll do correlation. Just let you know. So next week we'll talk about correlation, not this week. And that's true. Correlation does not imply causation, but that's not this stuff. That'll be next week. Right now, we're just seeing two different variables. And we think about the variable and you think about the survey question. So let me ask you, What season were you born in? Put it in the chat box. I can't imagine like you being afraid to tell people. Okay. I was born in the summer, by the way. Ooh, look at that. We're summer oriented in our group. I was born in the summer. But the point is that your answer to the survey question was not a number. I didn't say what season you were born in, and you didn't say 70 to 78 or something. You didn't say yes. This is again qualitative, and it's not a yes, no question. And then the other is what type of car do you drive? Sedan, SUV, or other? And if you think about that, that's not a yes, no question. It's not a number. You wouldn't say, oh, I drive in a 14. No, your car type is a SUV. Okay, it might be something different, but any questions on that? So now we have 2 survey questions, and both the survey questions are qualitative, and we want to see whether information about one is going to help you understand the other. Any questions on that idea? And I just want to note, we've seen these before in chapter 3, if you remember. Do you remember that? We looked at this kind of thing and we looked at independence and dependence. But we always focused on like just SUV versus winter being independent. But we're going to be doing something different now. Now we're going to have more capability. And now we're actually going to be looking at, in general, season and car type instead of a specific example. But reading the table is the same idea. So for example, this number 78 meant that 78 of the people that were surveyed were born in the fall and drive a sedan. Any questions on reading the table? Okay. So then once we have that, what we need to say what kind of test, what is the correct hypothesis test? What type of hypothesis test should we use? This is not a goodness of fit test. This is not saying is the distribution of one thing the same as some other known distribution. That's not what this is. This is 2 qualitative questions. And is there a relationship between the 2 or no relationship? More importantly, are they dependent or independent? So the test we're going to use is called the chi-squared test for independence. And we use that when we have 2 survey questions. They're both qualitative, and we want to see if they're independent. Any questions at all on the idea of the chi-squared test for independence? Any questions? Okay, so then we do step by step. We're used to this. So the next step is to state the null and alternative hypotheses. And here they are. H naught, the season a person was born in and the person's car type are independent. Notice I highlighted the word independent, saying it really loud. The season a person was born in and the person's car type are independent. Okay, which means that if you don't have that word independent, when I ask you what the null hypothesis is, then you lose points. For the alternative hypothesis, it's exactly the same, but instead of independent, it's dependent, because that's the opposite of the word independent. So the season a person was born in, and the person's car type are dependent. Must have the word dependent. Any questions on H naught and H1? And notice that there's no numbers in these things in terms of H0 and H1, no symbols, it's a sentence. So again, chapter 11, we're gonna have sentences. By the way, just a note, a heads up, chapter 12, we'll go back to symbols. So chapter 11 is a special chapter. Okay. So then you might be used to, the next step is we need to find the test statistic and the p-value. Any guess on how we're gonna do that? Yep, we're gonna have to go to the calculator. So I go to the calculator. This calculator will not work. This is the goodness of it calculator. So I'm gonna go back to the calculator menu. And this should be really obvious. What calculator number do we use? Yeah, this is calculator 22, test for independence. I tried to make it easy. If you can state the test you're using, then you just go to that calculator. Any questions on that? By the way, this is much easier than a handheld calculator. This kind of stuff is really hard to find and figure out. Okay, so the way I did it is I just have an A, B, C, D, E, first, second, third, fourth, fifth, sixth, seventh, and eighth. Okay, ninth and 10th. If you happen to have than more than 5 possible answers for each survey question, does that mean you can't use a test for independence? Any thought? So if the first question was what month were you born in, and the second was what country were you born in, that'd be a long list, okay? So the answer is you can still use the chi-square test for independence, but you can't use this calculator. But my spreadsheet calculator actually will work. There's the chi-square test for independence in the spreadsheet, and that one you can choose as many as you want. So that's just a note, is that goes for as much as you need. And there's other spreadsheet calculators that'll work too. Okay, but in terms of any question you're going to have to do on any of the exam questions or any of the assignments, you're not going to have more than this because it's just too much typing. So, but we do have to do some typing, so let's do it. And we have 73, 81, 76, 78. So we write 73, 81. And then 76, 78. And the next was 65, 68. And then 62, 64. And then finally, we have 43, 51. $48, $50. And let me just make a note, and that is if you happen to need to switch which are the rows and which are the columns, and do a what's called a transpose, then actually you can do that. It turns out the mathematics is independent of which one you're choosing as rows and which one you're choosing as columns, so that you're safe to switch, okay, if you needed to. All right, then we just hit calculate. And there we go. We have our chi-squared is about 0.48. And then the p-value is about 0.998. All right. Notice, by the way, our test stick is like way over here. And these are the level of significant, these are the values at which you can reject the null hypothesis if you're to the right of for the three different level of significance numbers. Okay. By the way, for chi-squared tests, all tests are right-tailed. You never have left-tailed because there's no left side. Okay, it stops at 0. It doesn't go forever on the left. So it's always right-tailed. So if your test statistic is to the left over here, it's always failed to reject. Okay. And I try to make it realistic. And hopefully you were all in agreement that you were guessing that what season you're born in has nothing to do with the kind of car you drive. Okay. By the way, is there anything, again, I have looked at lots of studies, think there's anything where what season of you were born in has any kind of dependence on something, of something else? Any thoughts? When you may have purchased a car, nah, that's just about very little to do with what season you're born in. Should I tell you? Things like how interactive you are in kindergarten. That would probably almost, I mean, I've seen statistics on that, and that actually has dependence. Any guess on why? There's a very, very sound reason for that. I don't see y'all jumping in. But if you were born, and especially nowadays, if you're born in the summer, nowadays, things were different when I was a kid and probably when you were kids too. But nowadays, if you're born in the summer, then that means you're actually the oldest kindergartner. Whereas if you're born in the fall, you're the, let's see, summer means, yeah, you're oldest, and sorry, summer means you're the youngest kindergartner, and fall means you're the oldest. Yeah, it used to be the opposite, actually. So and being older or younger when you're 5 years old makes a big difference, actually. Okay, and they've done that. If anyone wants to be a kindergarten teacher, you'll learn about that. Makes a big difference whether they're 5 or 5 3/4. So that would be an example where you would probably see a dependence instead of independence. But something like this is going to be independent. So we can make a conclusion. There is statistically insignificant evidence. Okay, hopefully you're used to the wording here because it's the same as we've been doing for the last 3 weeks. There is statistically insignificant evidence to make a conclusion that the season a person was born in and the person's car type are dependent. Notice you can just copy the H1 and just paste it right here. Make sure you uncapitalize the word the, and then you have your conclusion. Any questions on this example? Any questions? The wording is very different than the wording for good as a fit. So make sure that you pay attention and make sure that, again, one of the most important things is to be able to decide which kind of test you're going to be doing. And this example was a test for independence, a chi-squared test for independence. If you screw up and choose the wrong test, it'll be a disaster for you. So that is like the most important thing in this whole class, is to be able to decide on the test to use. Okay. And that's important for your future too, because if you're doing some research in your senior year of college and you end up using the wrong test, you just messed up. Any questions at all on this example before we move to the next one? Okay, let's go to the next example. And this is, do single men and women take the same type of vacation? Table below shows a study, shows the results of a study. Okay, and what we've got here is we got male and female. And we're going to call the three types of vacation: international, out of state, or more local. Okay. So those are the choices. And you can think about what's going on. The survey question, the first question they might ask is, what type of vacation do you like to take? International, out of state, or more local? And notice the three choices are very much quantitative. I'm not going to say 7. These are quantitative variables. So then the second question you might ask is, are you a single male or a single female or other? And if they're other, you just kind of ignore it. If they're married or something or whatever, or if they're a they, then we don't put them in for this example. Okay, other examples could happen, but not this one. All right. So I want to let you know that this is a different kind of test. It kind of has features of both of our other examples. So one feature you'll notice is we had 2 survey questions. They're both qualitative survey questions, and we looked at them. The other feature is that we're looking to see if the distribution of travel type or vacation type is the same for men and women. And that sounds like good as fit, right? So it kind of sounds like goodness fit. It kind of sounds like test for independence. It's not either of them. What we're looking at is we are looking at the distribution of travel for men versus women. But with this example, we don't know the population distribution for either. Whereas for our first example, we were given the population distribution for all of California, and we wanted to see the distribution for community college students. Here, we have 2 distributions and both are unknown, and we want to say, are they the same distribution as each other? Okay. Had it said is gender and vacation type, are they independent? Then you would use test for independence, but that's not what this asks for. This is comparing men and women. Do you see the difference? That's a problem a lot of people have, is to choose the test. Might be the hardest part of this whole chapter. Any questions on choosing? The variables are quantitative. Yeah, the variables are definitely qualitative. They're definitely qualitative. They're not quantitative. Because the survey question is, what type of vacation do you like? And you might say, I like more local. That's a word. And the other might be, are you male or female? And the answer is male or female. Do you see? Words. Do you see that? So it's very much qualitative. So the questions are both qualitative. So we're going to use what's called the chi-squared test for homogeneity. Do you know what the word homogeneous means? Like homogenized milk? Yeah, it's the sameness. So we want to find out, do we have the sameness in distributions? Or do we have different distributions? Do you see? So that's kind of what we're looking at. Okay. I want to give you a little history. When I actually first adopted the book, I've done a lot of consulting work for different agencies and organizations. And I found that the test for homogeneity was one of the most common tests that I needed to use in my consulting work. Okay, and I don't do some specialized thing. Just pretty much whoever asks me, then I'll help them out if I'm interested. And what I found is that test for homogeneity happened all the time. So when I read the book, it didn't have test for homogeneity in it. So I actually emailed the author, who I happen to know, saying, is there any way in the next edition you can put a chi-squared test for homogeneity? in the book. And you know what she told me? Any thoughts? Kind of a fun little story. And I had explained why I cared. All right, you're not saying? Here's the reason. Here's what she told me. Sure, we'll put it in the next edition. And can you write that chapter, that section? So she actually had me write. So that's the one section I fully wrote, is the test for homogeneity section in this textbook, in the OpenStax book that we use, elementary statistics. So I wrote that. I feel good about that. All the rest was written by Lasky and Dean. Okay. I put in all kinds of stuff, but I wrote that section. So, and pretty much everyone in California now makes sure that they teach that. Most of them teach that in their statistics class. All right, so the next thing we need to do. So does homogenizing have anything to do with it? Yeah, because homogenizing means that you're putting it all in together into one. So kind of makes them not different looking. It's all kind of mixed. That's what that kind of means. So it has something to do with it. So then we write down the null and alternative hypotheses. Okay, H naught. The distributions of travel type are the same for men and women. Notice that in our good as a fit, it's very similar, but instead of distributions, it's just distribution. So now we're going to say the distributions, because now we have two different distributions, men and women, and we don't know either of them. So, I'm sorry, distributions, travel type and gender. We don't know either of them. So we say the distributions of travel type are the same for men and women. And H1, the distributions of travel type are not the same for men and women. So very similar to the goodness of fit test in terms of the H naught and H1. Turns out the math is very similar to the test for independence. Okay, I'm not trying to be evil and be confusing. I'm just telling you kind of how things are. Any questions on H naught and H1? What do you think the next step is? What do you think? Yeah, go to our calculator. By the way, it's not a test for independence, so don't use that one. Go back to the calculator menu. This should be obvious. Which calculator number? Yeah, 23. And I want to let you know, this should make you smile. There's only a 24 and 25 left. That's it. We're almost done. As you might guess, next week, we're going to do calculator 24. And then week 11, which is our last week of new stuff, we'll do calculator 25. And that's it. This week we do 3 different ones. So I go test for homogeneity. And here I did it by A's and B's with 2 columns. And we got to put our numbers in. So we have the first column should be 29, 47, and 33. 29, 47, 33. So 29, 47, and 33. The second column should be 38, 42, 36. 38, 42, 36. So 38, 42, and 36. Okay. And notice, by the way, if you need more than these, this calculator won't work. Then you're going to have to go to my spreadsheet calculators, like for the projects, that'll work. There's others also. And then you calculate, that's it. And here we go. Chi-squared is about 1.40. And our p-value is about 0.496. And notice, by the way, we have the picture. We have our, 1.404 is over here. And notice to reject, you need to be far to the right than these guys, depending on whether you're using a 10%, 5%, or 1%. And we're not even close. So the conclusion is, hopefully you know that it always starts with there is statistically insignificant evidence to conclude, and that's because P is bigger than our level of significance. Okay. That, and then again, if you want, you can just copy H1 and paste it right here and make sure the is not capitalized. The distributions of travel type are not the same for men and women. Any questions? Any questions on this idea? Any questions? Any of you lost, or do you kind of see how these work? I do want to give you the heads up that it's always easier to watch someone else do it than to do it yourself. But it is important you practice and you do it yourself. Okay. And I do want to give you a reminder, and I reminded you on the orientation day, but I'm going to re-remind you since it's been a while. Your goal should always be to get everything done by Friday. So that way, if Friday happens and you realize you're not going to make it, then you can ask on Friday for extension. If you ask on Sunday for more time, like if your internet died or whatever it might be, you don't get extensions. You have to ask by Friday to get an extension. So that's just a note, because so you should really try to finish everything by Friday. Okay, let's do one more example. And here it is. A study was done asking 100 people who voted how many minutes they spent researching the candidate and the proposition. The mean was found to be 22 minutes, and the standard deviation was 8 minutes. The table shows the results. Is the distribution normal? Okay, this is going to be a little different. Any guess on what hypothesis test we're going to use? And a hint is it's going to be one of the three we just covered. Any guess? And if you have no idea, you got a 1 in 3 chance of guessing right. If you don't guess, you have a 0% chance of guessing right. So what's your best guess? See you all guess? Okay. So this one, let's take a look. The question is the distribution normal? So one thing, this is a question about distribution. So then, at least today, we had 2 different tests on distribution, good as a fit and homogeneity. But what we have is we have a known distribution that happens to be called normal. And we want to see if the distribution of minutes voted is the same as the given known distribution. Does that make sense? And that is good as a fit. It's not homogeneity, because that would be if we had 2 unknown distributions and we want to compare the 2. But here we have one that's known called normal. We have one that's not known called how many minutes did you spend researching when you voted. So because of that, what we're going to do is the following. Well, the mean was 22. The standard deviation is 8. So then we're going to use the empirical rule, basically. If you take 22 and subtract 8, you get 14. If you take 22 and add 8, you get 30. So I'm going to cut the results into 3 pieces. Less than 14, between 14 and 30, and greater than 30. Okay? And if I did that, you can just believe me or not, that the results I got were 20 were fewer than 14, 73 were between 14 and 30 minutes, and 7 were more than 30 minutes. Any questions on that? Just to make it easy, if you go 20 plus 73 plus 7, that would be 100. Do you see that? Because we asked 100 people. Then the empirical rule says that 68% should be within 1 standard deviation of the mean if you have a normal distribution. 68% of 100, hopefully you don't need a calculator for that, is 68. All right, any questions on that? All right, so then, if we want to say, what about this less than 14? Well, if there's 68% that are in this middle part, then there should be 100% minus 68%, which is 100 minus 68 is 32. 32 are on the 2 left outside, the left and the right. Half of the 32 will be on the left. Half the 32 will be on the right for the expected. Half of 32 is 16. So 16 less than 14 and 16 greater than 30. Are there any questions on how I came up with the expected values? Any questions? Okay, so once we have that, we know we need to use a goodness of fit test. We need to write down H naught. H naught will be the distribution of voter research time is normal. H1 is the distribution of voter research time is not normal. Any questions on this? Okay, we spent some time talking about, you have to assume you have a normal distribution. But we never talked about how you can tell. Okay, you can make it a histogram and look to see, hey, does it feel like it's normal? But feel like it's normal is never okay in statistics. You actually need to do mathematical calculations. And this is one way of doing mathematical calculations. Just to give you a little heads up, there is a much more sophisticated way of doing mathematical calculations. But if you want to learn that, any guess what you have to do? To learn how to do more sophisticated calculations for normal distribution? Yeah, transfer to university and take an advanced statistics class instead of an elementary stats class. So this is like, a very easy test for normal distribution, but there are actually more sophisticated tests, which they call the Komogorski test for normality. You don't have to actually know that for this class, but you might hear that someday in another class when you go to university. All right, so what we need to do now is we just need to go to the calculator. Not this one. Go back to the calculator menu. Scroll down, and it's good as fit because we already decided on that. The observed values are 20, 73, 7. Separated by commas. The expected values are 16, 68, and 16. and hit calculate. Any questions on that? Okay, so notice the chi-squared test statistic is about 6.43. So the test statistic, chi-squared, 6.43. When you do it on the assignments and the quizzes, it'll usually tell you how many decimals to take it. If it says 4, you need to go more. Just to let you know that. But if, you're just kind of looking at it, then whatever's told is fine. Okay, and then the p-value, 0.04. Just a note, let's suppose we're using a 5% level of significance. That seems reasonable, doesn't it? And we got 0.04. Okay. So in the real world, no one tells you what level of significance to use. Okay, the real world, you usually decide kind of based on your type 1 and type 2 errors and what field you're in and see what you need to do. So I'm just going to say, let's go 0.05 on this one. Okay. By the way, if the p-value was 0.05 and your level of significance is 0.05, what you need to do is you need to go more decimals. And eventually, you're never going to get exactly whatever the level of significance is. You'll either be below it or above it. Okay, so that's for sure. Always go as many decimals until you at least are lower or higher than level of significance. You're not going to be exactly equal ever. Okay, any questions on that? What do you think the conclusion is? What do you think the conclusion will be? Any thoughts? You could pop in the chat box. Could even write down the first few words. Yeah, there is statistically significant evidence because we're using 0.05. Don't say strong, because 0.04 is not smaller than 0.01. So, but there is statistically significant evidence to conclude that the distribution of voter research time is not normal. Okay. Any questions? Any questions on this conclusion? Notice that this last line, the distribution of voter research time is not normal, is literally H1. The distribution of voter research time is not normal. So once you have H1 written down, it's much easier to come up with your conclusion. I do want to let you know, if you're asked in chapter 9 or chapter 10 question, do not just write a sentence like this. Then for H0 and H1, then you need to actually have symbols. The conclusion of the sentence, but not the H0 and H1. Any questions on this whole chi-squared stuff? Any questions? Okay, and the best way to get good at this is to practice. Do your assignment, and if you're still not quite getting it, get a tutor to help, and then do some more practice from the assignment. You're always allowed to redo problems, and you never get nailed if you get it right, and then you redo it and get it wrong. You still get 100% if you got it right the first time. Okay, just let you know that. So it's important to practice. So the very last thing to do, any guess? Let's see, jumping in. The very last thing to do is give you the secret word. The secret word is chi, C-H-I, by the way, because we're looking at the chi-squared distribution. So I decided that chi would be a good word for the secret word for this week. And that is the important secret word. So I'm gonna hide it. Hopefully you wrote it down. And I will let you know that, again, it's a bit of an easier week in terms of the chapter, but I do expect you to start working on that project. Post in the project 1 discussion board, project 2 discussion board, your project idea. And then I'll let you know whether it can work or not. Okay, and if it can't work, I'll tell you maybe a suggestion to make some changes to make it work. Maybe I'll have to tell you, sorry, come up with something completely different. But usually there's some things you can do to change it. And make sure that, you have quantitative variables, should be a comparison of 2 quantitative variables where it makes sense to take an answer to one, an answer to the other, and subtract the 2. So they have to be the same units, for example. Okay, so that's important. So as usual, I'm going to stop the recording. Again, it's a little bit shorter than usual because I promised you.